Okay, so it's a pleasure to have for our next speaker, Pablo Shmerkin from the University of British Columbia, and he'll speak on improved bounds under dimensions of Furstenberg sets.
Okay, thank you. Thank you for the invitation. Thank you to Thomas and Henna for organizing this event, and to all the organizers of One World Fractals in general for this great series of events. Okay, so today I'm going to talk about joint work with Thomas Orponen and with Hong Wang. Separately, and in some sense also together, but mostly separately. But then let me start with some motivation for where this comes from, which is a problem in geometric combinatorics, so in a discrete setting. So if you have a set of points in the plane and a set of lines in the plane, a very natural question is, how many incidences are there between the points and the lines? And one way to measure this is by counting the number of ridge lines. So we start with a set X, it's a finite set, and for a parameter K, we consider the family of K ridge lines, which are the lines that intersect the set X in at least K points. So a line is ridge, so the set is given, a line is ridge if it intersects the sets in many points, where many is measured by this parameter K. And Semeredi and Trotter proved in 1983 that there are not too many ridge lines, so the number of ridge lines is bounded by a universal constant, and then there are two possible terms, one which is a boring one, which is the size of X over K, and one which is the fun one, which is the size of X squared over K cubed. And this is a really fundamental result in this area of mathematics. So it's really, it was really a breakthrough at the time, and it continues to have a lot of influence. And many related problems are still open. So, for example, what happens if instead of lines we consider circles? So it looks very innocent, but it is not so innocent. So the proofs, so there are proofs that are quite short, but that they are very ingenious. So this is not an easy theorem in the sense of it's very much not an exercise. So if you start trying to prove this, most likely you will fail. I don't want to say you will fail, but if you don't fail, you will have my respect forever. So it's took a lot of ingenuity to get this bound. So what is easy, and in fact it is an exercise that you may try to do after the talk, is to show that the bound holds with size of X squared divided by K squared, with a 2 instead of a 3 in the denominator, which is a Walsh bound, right? And this just uses the fact that 2 points determine a line. So, which is a very general phenomenon that holds in many other spaces where you have some concept of line and some concept of points. As long as 2 points determine one line, you will have the bound size of X squared over K squared for the number of K ridge lines. On the other hand, to get K cubed, one has to use a topology over 2. So this is not true in other linear spaces where 2 points determine a line. And in fact, for example, the analog of Semeredi-Trotter on finite fields is so vector spaces over finite fields, like two-dimensional vector space over a finite field. This is not known. There are partial results, but we are very far from having the sharp result. So I hope this all indicates that this problem is not as easy as it looks. Okay, and we have two bounds, size of X squared over K cubed, size of X over K. And we don't need both, so the theorem would be false, just keeping one of them. But the interesting one is really the one on the left. The one on the right covers boring situations, like if all points are just on one line or things like this. The fun bound is the one on the left that covers the interesting cases. Okay, so we are in One World Fractals. So now we want to do a fractal version of this. So we are going to consider, instead of a finite set X, a Borel set X in the plane. And we are going to look at ridge lines. So how do we determine if a line is ridge? Well, we look at the Hausdorff dimension. So we say that the line is S ridge if it intersects the set X in dimension at least S. And now we want to count how many ridge lines there could be. How are we going to count them? Well, again, by using Hausdorff dimension. And okay, so this is a space of lines, but lines are naturally parameterized by two parameters. For example, you can just parameterize by y equals mx plus b, and you identify this line with the parameter mb, the slope and the y-intercept. So that gives you the line. Okay, that doesn't give you vertical lines, but either you ignore vertical lines, which is not crucial, or you use another chart that doesn't include horizontal lines. Or there are other ways of parameterizing lines in R2, But in any case, lines are a two-dimensional manifold. So locally they are, so the space of lines is R2. So we can certainly talk about the dimension of a family of lines. And it's going to be a number between 0 and 2. All the lines in R2 have dimension 2, but there could be, of course, sparse set of lines. Okay, so the question is, what is the analog, or is there an analog of Semeredi-Trotter in this setting where we count things by dimension? So we would like to say that there are not too many rich lines in terms of S, the richness parameter, and the size of X measured by Hausdorff dimension. So I think this is a quite straightforward analog of Semeredi-Trotter if you want to do fractal geometry. Okay, so normally the problem is not stated in this way, so I'm going to move on to the way it's usually stated, but I want to emphasize that it's really the same problem. So essentially there are three parameters. One is S, which is the richness parameter of the lines. So the line intersects the set in dimension S. The second parameter is the size of the set X of points. And the third parameter is this number T, which is the size of the rich lines. Always measured with dimension. Okay, and we would like to say that there are not too many rich lines, but an equivalent formulation is asking or trying to prove that if there are many rich lines, it's because the set itself must be large. So this is really equivalent. So there are three parameters, and we want to bound one of them in terms of the other two, but one can do algebra and bound T instead of U. But in the normal formulation, we try to bound U. So the usual formulation is in terms of this definition. We say that the planar set is a TS Furstenberg set if there is a set of lines with dimension at least T. Again, I'm not saying that the union of the lines has dimension T. I'm saying that the parameters giving you the lines has dimension T. In fact, this is equivalent to saying that the union of the lines has dimension 1 plus T, but this is not the right way of, which is a theorem, but this is not the right way of thinking about this. Okay, so we have two parameters, T and S. T measures how many lines we have, and S measures the richness of the intersection. So the set X intersects each line in this family in dimension at least S. And we would like to say that such a set has to be large, depending on T and S. We would like to give a formula in terms of T and S that is a lower bound for the dimension of X, right? Because if there are many lines intersecting a set in many points, the set should be large. So this is intuition, and we would like to make it quantitative, and ideally find this number UTS. Unfortunately, in general, it's very hard, very hard to find this number UTS, so this is an extremely challenging open problem. But today I'm going to talk, or I'm talking about some partial progress. Okay, so what is known about this problem? Actually, many things are known, and actually I'm not going to mention all of them for lack of time. So here is again the definition of what we are looking at. We are looking at the smallest possible Hausdorff dimension of a set that has a large intersection, dimension S, with a large set of lines of dimension T. Okay, and there are two bounds that I'm calling classical bounds obtained by these people let's say by these people altogether. So the first bound is S plus the minimum between S and T, and the second bound is S plus T over 2. Okay, so these ones are classic, I call them classical, even though the Lutz-Tour result is only a couple of years old, few years old, but they use elementary, I'm not saying they're trivial or anything, but they use elementary methods. They don't use big machinery. And actually, when T is at most S, so the number of lines, the dimension of the set of lines is at most the dimension of the intersection of each line, this is sharp. It's quite easy to see that it's sharp. Okay, but in other cases, it was not expected to be sharp, and this is the topic of today's talk. So some indication that this might not be sharp is that if T is equal to 2S, if T is equal to S first, if T is equal to S, then the left-hand side bound is larger and it is 2S. So when T is equal to S, the bound given by these classical methods is 2S. But if we increase T from S to 2S, so we double the dimension of the set of lines. All the parameters are positive here, by the way. This is not so interesting if T or S is 0. So I'm always assuming positive. Okay, so if we increase the dimension of the set of lines from S to 2S, this bound doesn't change. It's still 2S. And this shouldn't be true. Okay, so this is a bound, so it is true, but this shouldn't be sharp because the more lines you have, the bigger the set should be if it intersects more and more lines in a large set. But this is not reflected by these lines. And also, when you have two different bounds, an interesting case to consider is that in which they coincide, and they coincide when t is equal to 2s. Okay, so a very important result of Bourgain, but really is a combination of Bourgain and a previous paper of Katz and Tao, says that the previous bound is not sharp in the particular case when t is 1 and s is 1/2, in the sense that there exists a universal constant epsilon such that 1/1/2 Furstenberg set has dimension at least 1 plus epsilon. And these bounds are both 1 when s is 1/2 and t is 1. And it corresponds to the case when t is 2s, s is 1/2, t is 1. Okay, so this is a very difficult theorem, as you could imagine just by looking at the authors of these papers, but it is, okay, because it's not that they realize there is some simple idea that does it. It is actually difficult. Okay, and for quite a long time, this was the only improvement over the classical bounds. By the way, this predates some of the classical bounds, but this is not important. So this was the only improvement over the classical bounds for quite a long time. And then with Cornelia Hera and Alexia Iavicoli, we proved that the same is true, not just when s is 1/2, but for any value of s positive. So s is a number between 0 and 1 because it's the intersection of a line with the set. So it is at most 1 because the intersection is contained in a line. S is between 0 and 1, t is between 0 and 2 because it's a dimensional set of lines, which is a two-dimensional space. Okay, so what we did is basically extending the theorem of Bourgain to other values of s rather than just 1/2. And we follow the same proof, but okay, the proof is not so easy, so we had to work a bit. Also, there were some parts of the proof that we didn't understand, so we had to figure out what to do. And then Daniel Di Benedetto and George Zal, they obtained an explicit and I would say reasonable, like 1/10,000. This is reasonable in this area, explicit value for epsilon of s. So in the previous works, the value of epsilon is not explicit. Okay, but in all these works, it is absolutely crucial that t, the size of lines, is 2s, s, the size of the intersection of a line with the set. So this equality forces a lot of structure on the set that allows us to get some information, which is the key idea of Katz and Tao, actually. And you don't have that if t is not equal to 2s. Okay, so now come the new results. Here, I recall what was known before. First, we have the classical bounds. Second, we have the epsilon improvement, but only in the case when t is equal to 2s. And the new things are that with Thomas Orponen, we prove that whenever t is bigger than s, but it could be just a little tiny, like a little bit bigger than s, just a tiny bit bigger, there is an epsilon that depends on t and s, such that we get an improvement over the previous classical bound 2s. So in other words, in the case of U2s, we obtain this improvement, but t has to be much larger than s. It has to be double the size of s. Here, t has to be any number larger than s, even just a little bit larger, and we get the same result. Of course, the epsilon will depend also on t in this case. So this is the first result, and actually using the proof of the previous result, later with Hong-Wang, we obtained a similar epsilon improvement for the other classical bound. For the s plus t/2 bound, we essentially showed that this bound is also not sharp. We can add an epsilon that depends on t and s. Let me say at this point that there are other bounds that I'm not mentioning in this talk, in particular when t is larger, quite a bit larger than 1. And in some cases, this has been fully solved by Kevin Wren and Yuki Fu. So there are other bounds, and somehow the case when the size of the set of lines is large, other techniques come into play, and the situation is a bit different. So there are better bounds obtained with harmonic analytic techniques. Okay, so now I want to make a point, maybe a philosophical point, that is well known in some areas in analysis, but maybe not in others. So maybe this is a good point to make to this audience. So first of all of these results are proved by discretizing the statement. So the statements are about house of dimension, but instead of working directly with house of dimension, we first come up with a version of the problem that makes sense at a given small but positive scale delta. For example, lines are going to be replaced by delta tubes. A delta tube is a delta neighborhood of a line. So we thicken everything by delta. And instead of house of dimension, we have to replace it by something that tells us that the set looks like is dimensional, but at scales between delta and 1. And I'm going to state this condition in the next slide. Okay, so in order to prove the results, we need to discretize. But this is not the key point I want to make. The key point I want to make is the next one. Not only is discretization essential to prove the results, but the real results are the discretized ones. So the house of dimension statements should be seen as corollaries, which are in some sense not as interesting corollaries of the discretized results. What really matters is the discretized results. Why? Because there are many other problems in this area of discretized geometric combinatorics, including some famous ones. If you haven't heard of these problems, just trust me that they are all famous problems. Maybe the radar projection problem became better known in recent years, but the other three have been known for a long time. And these problems are all closely connected. In fact, what Katz and Tao's contribution in this paper that I mentioned before is realizing how the discretized versions of these problems are connected. So they didn't prove anything. They proved equivalencies between discretized versions, but this turned out to be extremely influential. So if one wants to use tools from one problem to make progress on another problem, one has to do it via the discretized versions. You're not going to be able to do it via the house of dimension versions. So the house of dimension version usually is easier to formulate, so it can give you some intuition or heuristics about how to connect the problems. But if you actually want to connect the problems, you need to go back to the discretized formulation. So it is a discretized formulation that is really the core of what's going on in all of these problems. So let me state a discretized formulation of one of the results, the one I obtained with Thomas Orponen. Well, first of all, this condition of delta, this definition of delta S is set, is essentially saying that a set has house of dimension S at scales between delta and 1. Okay, if you haven't seen it before, maybe it's too much to absorb, but essentially it's like a Frossman condition where, okay, so what is this bar delta is the delta covering number, the smallest number of delta balls needed to cover a set. And this delta covering number satisfies a sort of Frossman condition. So hopefully, at least at some level, you agree that this has something to do with house of dimension. But we cannot do house of dimension because these are sets that could be union of, so I'm thickening everything by delta. So the sets themselves are union of delta balls. The house of dimension is full. This is not what I'm interested in, but I want to see from scale delta to 1 how it looks like, and I want to make sense of the fact that at those scales, or at this scale range, the set look is dimensional, and this is a way to do it, which has appeared in many papers going back to Katz and Tao. Katz and Tao used a slightly different definition, but it's the same concept. Okay, so actually one has to be careful with this because on the one hand, it is morally true that if you take a real set of dimension S, a compact set of dimension S, and you discretize it at scale delta in the correct way, you get something satisfying this. But the opposite is not true. Not every delta SC set arises as a discretization of a real fractal, so which causes problems or almost counterexamples in some cases. But nevertheless, this is the definition that we work with. Okay, and now we discretize the notion of Furstenberg set. In Furstenberg sets, we have a set that intersects many lines in a large set. Okay, so now we discretize it, so we have the scale delta, we have the parameter C. So C is a parameter that tells us how much leeway we have in this Frossman condition. The bigger the C, the more flexible this Frossman condition is. So we just replace house of dimension on the set of lines and on the intersections by delta T C sets and delta C S C sets. Except for the intersection of the set with the line, rather than asking it to be a delta SC set, we only ask it to contain, which makes sense because it gives more flexibility. If it contains a delta SC set, then it is large. Okay, so unlike out of dimension, it's not true that if a set contains a delta SC set, it is automatically a delta SC set. If a set contains a set of dimension at least S, it has dimension at least S. But at this discretized level, you see things are not so simple, so we have to assume this. Okay, so now we have more parameters because we have TS, but as before, but we also have delta, we also have C. Okay, so delta is going to tend to 0, but it is our scale. And C, you should think of as a constant, but as we will see in the next slide, it is sometimes true and important that C actually can grow with delta. As delta goes to 0, C can grow. This is important. Okay, so here is a discretized version of one of the epsilon improvements on Furstenberg's problem. It corresponds to the improvement over the bound 2s over the classical bounds, and it says the following. If instead of having a TS Furstenberg set, we have a discretized one, so delta TS and C is delta to the minus epsilon. So as you can see, this C is allowed to grow exponentially, a small exponential, but epsilon is a fixed number, it's positive. So it depends on T and S, but it's a positive number. So this really allows C to grow, which gives us a lot of flexibility, which is actually very important in all the connections and applications. But nevertheless, the conclusion is that delta TS, delta to the minus epsilon Furstenberg set, so a set that contains a discretized S-dimensional set for a discretized T-dimensional set of lines is very large. It has size at least delta to the minus S minus epsilon, and this morally says that the box dimension of X is at least 2S plus epsilon, but in fact, by a well-known argument that we wrote down in detail with Cornelia and Alexia, we get Hausdorff dimension as well out of this discretized statement. Okay, and with one, we have a similar discretized statement, very similar. I'm not stating it here. Okay, so the paper with Thomas Robben is quite long, so I only want to highlight a couple of aspects of the proof. So the starting point is a previous important paper of Thomas, where he proved that the packing dimension of TS Furstenberg sets is at least 2S plus epsilon. So same result, but for packing dimension instead of Hausdorff dimension. So one night I was looking at Thomas's proof, and what I realized first is that the arguments actually show something a bit stronger. So if you go to the discretized statement, so this is again a case where you really have to look at the discretized statements to make further progress. In the Hausdorff dimension or packing dimension version, there is nothing to do, but looking at how Thomas proved the packing dimension version. So actually, Thomas was working with two scales, scale delta and scale square root of delta. And okay, so in fact, if the set, so if you look at the discretized version, and the set has this property, which is some sort of regularity, but kind of very weak regularity, that the size of the set at scale square root of delta matches the exponent, sort of the dimension of the set. This is in some sense like saying that the box dimension of the set of lines is equal to the Hausdorff dimension of the set of lines. Something like this. It's actually much weaker than that, but that's one way of thinking about it. Okay, so under this additional assumption, which is sometimes true and sometimes not true, one gets an epsilon improvement for the Hausdorff dimension. This is all discretized, so this is why it's between quotes. Okay, and then together with Thomas, we did two things. One is that given a general set of lines, so L is a set of lines, we were able to produce a multiscale decomposition. So a multiscale decomposition is just a sequence of scales, finitely many scales, starting with delta, the given scale in our problem, and going up to 1, in such a way that we have a sort of dichotomy. For some scales, or for some scale intervals, really, because you should think that you go from one scale to the next, and you only look at the set between those scales. Anyway, I really don't want to go into details, because even defining what this means would take way too much time than I have. But the idea is, for some scale intervals, actually the set satisfies this regularity condition, and then locally at those scales, we get this epsilon gain. And this happens for enough scales. So in some sense, there is an epsilon proportion of scales, something like this, where we have this epsilon gain coming from essentially the argument in Thomas's previous paper. Okay, and what about the other? So certainly we cannot guarantee, and it is not true, we cannot guarantee because it's not true that the set is going to be regular in a suitable way for all scales. So we have the other scales where it is not regular, but essentially at the scales where the set is not regular, we just use the classical bound. So the classical bound is 2s, the improved bound is 2s plus epsilon. So at some scales, we have 2s plus epsilon because of the regularity. At the other scales, we have 2s. We don't gain, but we also don't lose. But at positively many scales, we do win an epsilon. And the next ingredient, which is also a crucial ingredient, is a way to combine all these scales together to get something about the actual set, not between two little scales, but globally for the whole set. So we have a new sort of incidence theorem that combines all the scales together. Okay, I know this is very vague, but just to give some very rough idea of what is involved in the proof. And again, it shows the importance of looking at the discretized statements, because just knowing that the packing dimension of Furstenberg set is 2s plus epsilon is useless. But if you look at what Thomas really proved in a discretized way, so that was the starting point for our project. Okay, and I have 4 minutes left, so I want to mention that this epsilon improvement for Furstenberg sets already has had quite a few number of applications, and I want to emphasize in particular that in many of these applications, it's not an epsilon gain, it is an explicit gain, and in some cases even sharp results. So even if you start with an epsilon gain, sometimes you can parlay that into an explicit, large, and even sharp, in some cases, gain. Okay, and these are just some keywords, and if you don't know any of these things, don't worry. I just wanted to make the point that this is actually useful. It's not just interesting on itself, by itself, hopefully, but it has had a number of applications. So there is a little bit of cheating here, because really the second, third, and fourth points use the first one. So our indirect applications via radial projections. But ultimately, the radial projections improvement depends on this epsilon improvement on Furstenberg's problem. And I want to say that all of these works require, so it's not a direct application, it's not a corollary. So they use the epsilon improvement in Furstenberg's problem, but there are many other things involved in all of these problems. Okay, and that's all. Thank you very much for listening.
Thanks a lot, Pablo. Does anybody have any questions?
I'll ask a question, Pablo. So there were some results where you said it was very important that T was equal to 2s or something like that, if I remember rightly. Can you give us just a brief bit of intuition as to why that's a special case, or how that's used?
So when T is equal to 2s, essentially you can manipulate things. Okay, so you basically do a control assumption. So when T is equal to 2s, you assume that the dimension is extremely close to 2s, and you do it in a discretized way. Otherwise, it doesn't work. But right, so we are talking about this bound. So when T is equal to 2s, you assume that the dimension in a discretized sense is extremely close to 2s, and using the argument of Katz and Tao, you eventually, after lots of work, you deduce that the set looks like a Cartesian product set after some change of coordinates. And that's an additional structure that allows you to apply something called the discretized sum product theorem. So essentially, the idea is that if T is equal to 2s and this bound doesn't hold, then essentially, for every point in the set, all of the lines through it intersect the set in dimension S. So something that a priori happened for some lines actually happens for every line. So something like this. There is some sort of saturation that eventually, after a projective transformation and lots of refining, tells you that the set is like a Cartesian product. And then you still have to work a lot more to reduce it to the sum product theorem. I know this doesn't really answer the question, so it's really not easy, but if I could draw some pictures and I was feeling better, I could tell you more. So maybe I can tell you more at some other point.
Thanks, Pablo.
Thanks. So does anybody else have any questions?
I don't really
Yeah,
have a
can't-
question, but I just want to see the discretized version, the delta SC set again.
Okay, so do you want to see the definition of delta SC set?
This thing, yeah,
or
yeah,
the
because you were
statement?
saying,
Yes.
so okay, so I can see how this is morally, I can see how this is morally the same, morally the discretized version of it being S-dimensional. I don't understand why C plays a role in the statement. You were saying that somehow these all become like genuine parameters. But if you were doing...
Okay, so if you have a Furstenberg measure, there is a C which is associated to the Furstenberg measure, and
Yeah.
you treat it as a universal C.
Yes.
But here you have more freedom because you have this parameter delta, which you don't have access to when you talk about
so you
Gaussian
think,
dimension.
so you fix delta. So somehow C is actually, well, C and delta, they come as a pair. And so there's a genuine dependence between the two. Is that what you're saying?
What I'm saying is that it can work in your favor to have this dependence, or it can give you a stronger statement. So the larger the C, so the way to think about this is that the larger the C, the weaker this condition is. So you have more sets satisfying this assumption. So if you make a statement about all the sets satisfying this condition for a larger C, you have a stronger statement. And in our result, and in many other results, C can grow exponentially with delta, like small exponentially with delta. That makes the result stronger in a way that is extremely useful in applications and in transferring the ideas from one problem to another.
Okay, I see. I was thinking that it would be somehow an enemy, but you're actually saying that it's an ally.
Yeah, so there are many more delta TS, delta to the minus epsilon Furstenberg sets than delta TS 1 million Furstenberg sets.
Yeah.
So our result applies to many more sets. And this is
Okay.
actually useful. It's not just a technical thing that just happens to work in the proof. Well, it is. It's something technical that happens to work in the proof, but it's also useful.
Yeah, okay, I see. Thanks. Thanks a lot.
Mm-hmm.
Okay, so are there any other questions? Okay, then if not, let's thank Pablo once more. And I'll stop recording and see if that magic key induces any questions.